Hello everyone and welcome back to Math 220A Mathematical Logic. Lecture 26 Uncountably Categorical Theories. In the previous lecture we have discussed the class of countably categorical theories with a unique countable model up to isomorphism, and we have isolated several equivalent characterizations of this class of theories. Today we move into the realm of uncountably categorical theories. The following is a fundamental theorem of Morley from 1965. Let T be a countable complete theory which is kappa categorical, i.e. has a unique model of cardinality kappa up to isomorphism for some uncountable cardinal kappa then T is kappa categorical for every uncountable kappa. This fundamental theorem is often viewed as the beginning of modern model theory, where the focus shifts from studying logics to studying complete theories and their properties. And it introduces a number of very important tools and ideas of stability theory, which have since found a lot of other deep applications. Example: let T infinity be the theory of an infinite set in the language of equality with no additional structure. Then this theory is uncountably categorical. Indeed, every model of T infinity is determined up to isomorphism by its size, since isomorphisms for such models are simply bijections between the base sets. Example 2. Let kappa be a countable field and let VSK be the theory of vector spaces over K in a language containing a function symbol for multiplication by each scalar from K and vector addition and subtraction. So again, we have that the theory is kappa categorical for all uncountable kappa. And the reason here is that by linear algebra, two vector spaces of the same dimension are isomorphic, and the dimension of an uncountable vector space over a countable field is just its cardinality. And hence any two vector spaces of the same uncountable cardinality over countable field have the same dimension, so they are isomorphic. And similarly, same holds for the theory of algebraically closed fields of prime characteristic or characteristic 0 with the transcendence degree over the prime field in the place of dimension for vector spaces. So here we have a similar result from field theory, that such a field is determined up to isomorphism by its transcendence degree over the prime field, which is countable here. So we get an analogous result. These are three typical examples of uncountably categorical theories. And as we will see, there is a unifying principle which abstracts the theory of dimension, the dimension in vector spaces or transcendence degree in algebraically closed fields, which allows to prove similar categoricity result for an important class of theories, the so-called strongly minimal theories that we are going to discuss next. Let us first recall a couple of properties of the algebraic closure operator. So let M be a structure and A a subset of M. Then the algebraic closure of A in M is given by the set of all elements little a in M, such that M satisfies phi of A for some formula phi of X with parameters in the set capital A, and such that the set of solutions, the total set of realizations of the formula phi in M is finite. Elements of this form are called algebraic elements. So the algebraic closure is the collection of all elements algebraic over A. And we will also say that A is algebraically closed if it is equal to its algebraic closure. Remark: 1. Given A subset of M, which is an elementary substructure of N, we have that the algebraic closure of A in the sense of M is equal to the algebraic closure of A in the sense of N. Indeed, an L of A formula phi of X such that the set of its solutions in M is finite also satisfies that the set of its solutions in N is finite, and in fact we have that the set of solutions is exactly the same. This follows by elementarity because the A theory of M says that there exists at most n elements satisfying phi for some fixed number n, and the same must hold in n, so this means there are no new elements that can appear in the set of solutions of phi in n. Hence, from now on, we will omit the subscript in the notation for the algebraic closure. And 2, the algebraic closure of a set A is also equal than the maximum of the cardinality of the set A and the cardinality of the language. So this is straightforward because for each formula, of which there are only L many, we only can have countably many sets given by this formula in the algebraic closure. Example: if M is a model of the theory of infinite sets, then the algebraic closure of any subset is just the set itself. This follows from quantifier elimination, as every formula is just a combination of equalities and inequalities, and the ones with finitely many realizations are the equality ones. Another example, assume that M is a vector space over a field K, then a vector A is in the algebraic closure of a set of vectors capital A if and only if A is in the linear span of the set capital A, and 3, if M is an algebraically closed field of some fixed characteristic, then A is in the algebraic closure ACL of A in the sense of model theory, if and only if A is in the field theoretic algebraic closure, meaning that there is a polynomial with coefficients in the field generated by A and such that A is its root. Definition: a type P over a set of parameters A is called algebraic if P contains an algebraic formula. That is a formula with parameters from the set capital A, which only has finitely many solutions. Remark: 1. Any algebraic type P is isolated by an algebraic formula phi of x in P with the minimal number of solutions in M. So this is a little exercise that any such formula with the minimal possible number of solutions in P isolates the type, and then using this remark 1 and compactness, we can see that a type P in S of A is algebraic if and only if P has only finitely many realizations in any n an elementary extension of M. And in fact, it suffices to verify that P has only finitely many realizations in an arbitrary elementary extension n containing the set of parameters A, which is the cardinality of A plus saturated. Next, we discuss strongly minimal formulas in theories. Definition: let M be a model of T, which we assume to be a complete theory with infinite models in a countable language, as usual, and assume that d of x is a formula with parameters in M, which is non-algebraic. Then 1. The set of the solutions of D in M is called minimal if for all psi of x, a formula with parameters in M, we have that the intersection of the set of solutions in D in M with the set of solutions of psi in M is either finite or cofinite in the set of solutions of D in M. 2. We say that the formula d of x is strongly minimal if the set defined by this formula d of n is minimal for every n an elementary extension of M. And 3, we will say that a theory T is strongly minimal if the formula x equals x is strongly minimal in T. For example, each of the theories T infinity of an infinite set, vector spaces over fixed field K, or algebraically closed fields of fixed characteristic are strongly minimal. This follows from our quantifier elimination results in each of the cases where we can see that all sets in a single free variable are either finite or cofinite. Let us be careful, however. Minimality is different from strong minimality. For example, let L be the language consisting of a single binary symbol E, and let M be an L structure in which E, M is an equivalence relation with one class of size n for all n in omega and no infinite classes. Then we can check that x equals x is a minimal formula in M, meaning that every definable subset of M is either finite or cofinite, but by compactness there exists n, an elementary extension of M, such that some element A in this elementary extension has an infinite equivalence class but then if we look at the set En of A, so the set of all elements of n that is in the same class as A, this defines an infinite, co-infinite subset of n. So this shows that the formula x equals x is not strongly minimal in T. The theory of M in the language L. Another remark, the property phi of xa, where a is some parameter, is strongly minimal, depends only on the type of the parameter a of the empty set. Namely, we have that phi of xa is strongly minimal if and only if for all psi of xz in L, where z is an arbitrary finite tuple of variables, the set sigma psi of za, which we can take to say there exists more than k x phi of xa and psi of xz holds, and there exists more than k x such that phi of xa and not psi of xz holds, and we consider such formulas for all k in n natural number. So this is an infinite set of formulas, sigma psi, and strong minimality guarantees that this set of formulas cannot be realized in any n, an elementary extension of M. Hence, by compactness, this means that for all formulas psi of xz, there is a bound k psi such that M satisfies for all z. Either we have that there exists at most k psi elements x such that phi of xa and psi of xz holds, or there exists at most k psi x such that phi of xa and not psi of xz holds. So for any choice of z, either the set cut out from phi by psi or by its negation has size at most k. And this is of course an elementary property of the element A expressed by a formula. Hence, it makes sense to say that the formula phi of xb is a strongly minimal formula without specifying the model. In which we are talking about this formula being strongly minimal. An immediate corollary of this, assume M is a model of T, which is aleph naught saturated, then any formula phi of x with parameters in M such that phi of M, the set of its solutions, is minimal, is strongly minimal. So with some amount of saturation, minimality and strong minimality coincide. Proof: if M is aleph naught saturated and phi of xa is not strongly minimal, then for some psi of xz, an L formula, the set defined in the remark sigma psi of za is realized in M, and so we have that phi of M is not minimal. Exercise: if M is strongly minimal, so in the sense that the theory of the structure is strongly minimal, A is an arbitrary subset of M, and we have that taking N to be the algebraic closure of A, this algebraic closure is infinite, then in fact N is an elementary substructure of M. So all infinite algebraically closed sets are elementary substructures. This can be verified using the Tarski-Watt test. This exercise already hints that the algebraic closure operator is particularly well behaved in strongly minimal sets. So given M, an L structure, and assume that d of x, a formula with parameters nm, is strongly minimal, then we consider the closure operator CL closure as a map from the subsets of the set of solutions of this formula in M to the set of subsets in M defined by the closure of A is the algebraic closure of the set A intersected with D of M. So we take the relative algebraic closure relativized to the set of solutions of this formula D in M. Then we have the following proposition. The closure operator CL satisfies the following for all A subsets of D of M and AB elements of the set D of M. 1. Reflexivity. A is contained in its closure. 2. Finite character. The closure of A is the union of the closure of A prime, where A prime is an arbitrary finite subset of A. 3, transitivity. So we have that the closure of A is equal to the closure of A. 4, the most important property which relies on strong minimality is the exchange property. If A is an element which belongs to the closure of A together with an additional element B, but not to the closure of A alone, then B also belongs to the closure of A together with the element A. So here we are abusing the notation slightly and write A concatenation little a. So we write AA to denote A together with a set consisting of a single element A. This is a standard abuse of notation which doesn't introduce any ambiguity typically. Proof. Properties 1, 2, 3 hold without any assumptions on the theory or on the set D, the formula D of x. 1 and 2 are straightforward from the definition of the algebraic closure operator. So we check first 3. Assume that C belongs to the closure of some set B1 through Bn, and each Bi belongs to the closure of the set capital A. We let phi of x B1 through Bn be a formula in L with parameters in AB bar, the tuple of B1 through Bn, be an algebraic formula with finitely many solutions satisfied by C. Then we let phi I of y be a formula with parameters in A, and we let it be algebraic, satisfied by the element Bi. Then we can take psi of x to be the formula exists y1 through yn, such that we have phi I of yi holds for all I from 1 to n, and there exists at most k z such that phi of z y1 through yn and phi of x y1 through yn. We see that this is an algebraic L of A formula satisfied by C. So this shows that C is actually algebraic over A. On the other hand, property 4 is more subtle and relies crucially on the assumption that the formula D of x is strongly minimal. So suppose that A belongs to the closure of AB, but not to the closure of A alone. Then we have that M satisfies phi of AB, where phi of xy is some LA formula, and we have that the cardinality of the set of the realizations of phi in D, where we plug the parameter b, is equal to n for some natural number n. Since so we pick a formula which witnesses that A is algebraic over the set capital A together with the element b. Then we let psi of A be the formula expressing that there exists exactly nx such that d of x and phi of xy holds if psi of D, so the set of solutions of psi in D, is finite. Then we have that B belongs to the closure of A by the definition of closure, but hence we also have that A belongs to the closure of the set capital A alone, as in the argument for 3. But this is a contradiction, because we're assuming that little a is not algebraic, not in the closure of the set capital A. Thus, we have that psi of y defines a cofinite subset of D. Since it's not finite and D is strongly minimal, it has to be cofinite. Now, if the set of y in D such that phi of ay and psi of y holds, so if the set of all such y is finite, we are done, because then B belongs to the closure of the set capital A together with the element little a. So from now on we may assume that the set of such y is infinite, hence cofinite in D by the assumption of strong minimality. So towards a contradiction, assume that D minus the set of all such y such that phi of ay and psi of y holds is equal to L for some natural number L. Then we let chi of x be the formula expressing that there exists exactly L y such that d of y holds and the negation of phi of xy and psi of y holds. Now, if this formula chi of x defines a finite subset of D, then we would have that A is in the closure of the set capital A, because A does satisfy this, but this is a contradiction again. Thus we have that chi of x defines a cofinite subset of D. Now we can choose A1 through an plus 1 such that chi of ai holds. This is of course possible. We can choose any number of such a's because the set is infinite in D. In particular, we can choose n plus 1 many, where remember n was the cardinality of the set phi of dB. Then we have that the set bi consisting of all y in D such that phi of aiy and psi of y holds in M is cofinite for all I from 1 to n plus 1. Then we can take an arbitrary element b prime in the intersection of all the bi's. Each is cofinite, so the intersection is of course non-empty. Then we have that M satisfies phi of ai b prime for each I. So we conclude that the cardinality of x in D, for which we have that phi of x b prime holds in M, is greater or equal than n plus 1. But this contradicts the fact that psi of B prime holds. But remember that psi of y was defined to be the set of all y's for which the set of solutions of phi of x y is exactly n, has exactly n elements in it, and we have found some parameter b prime which has at least n plus 1 solutions. So this is a contradiction, hence this concludes the proof of the exchange property of our closure operator. Now we have definition. Any abstract closure operator CL from the subsets of a set X to the subsets of a set X on X infinite, satisfying the properties 1 through 4 from the previous proposition, is called a pregeometry, sometimes a combinatorial pregeometry, if the underlying set X is finite. Then such an operator, the closure operator, is called a matroid. There exists a rather rich theory of matroids in combinatorial geometry. So what is important for us here is that working in an arbitrary pregeometry, one can develop notions of independence, dimension, basis, etc., generalizing the familiar linear independence in vector spaces or algebraic independence in algebraically closed fields. But here we can work in an arbitrary, strongly minimal set. Let's make some of these ideas precise. Definition. Let a set D, together with a closure operator on it, be a pregeometry. Then a subset A of D is called one independent over C if A is not in the closure of the set A without the element little a, respectively, if A is not an element of the closure of C together with A but without the element little a, and so that this holds for all a little a in the set capital A. 2, we say that capital A is a generating set for y a subset of D if we have that A is a subset of y and y is equal the closure of the set capital A, and finally 3, A is a basis for y a subset of D if A subset of y is an independent generating set of y. Note, any maximal under inclusion independent subset of y is a basis for y. So this follows immediately from the definitions. And just as in vector spaces, we have the following replacement lemma. Assume that A, B are two subsets of D, independent, with A contained in the closure of B. We have one, suppose A0 is a subset of A, B0 is a subset of B, and A0 together with B0 is a basis for the closure of B and A belongs to A but not to A0, then there exists some B in B0 such that A0 together with the element A and together with the set B0 but without the element little b is a basis for the closure of the set capital B. In particular, this implies that A has cardinality less or equal than the cardinality of B, and 3, if A and B are both bases for some set Y, a subset of D, then they have the same cardinality. Proof 1. Let C be a subset of B0 of minimal cardinality such that A belongs to the closure of A0 together with this set C. As the set capital A is independent, the cardinality of C has to be at least 1, and we let B be an arbitrary element of the set capital C. By the exchange property, we have that B must belong to the closure of A0 together with the element little a together with the set C without the element little b. Thus we get that the closure of A0 together with little a together with B but without the element little b is equal to the closure of the set capital B. But now, if A belongs to the closure of A0 together with B0 but without the element little b, then we would conclude that B belongs to the closure of A0 together with B0 minus B. But this contradicts that A0 union B0 is a basis for the closure of B. Thus we conclude that the set A0 together with little a together with B0 minus little b is independent, and we already know that the closure is equal to the closure of B, hence it is indeed a basis for the closure of B. To show 2, suppose that B is finite. Say the cardinality is equal to n, and let A1 through an plus 1 in the set A be distinct. Let A0 be the empty set, and let B0 be the set B. Now, using 1 inductively, we can find elements B1 through Bn in B pairwise distinct, and such that we have that the set A1 through AI together with the set B but without the elements B1 through Bi is a basis for the closure of B, and so that we have it for each I less or equal than n. But then we get that the closure of the set A1 through An is equal to the closure of B, and as a n plus 1 also belongs to the closure of B, this contradicts the independence of the set capital A. So this gives the proof in the case of a finite B. Now suppose that the set capital B is infinite. Then for any finite B0 subset of B, we have that A intersection with the closure of B0 has cardinality less or equal than the cardinality of B0 by the previous paragraph. So in particular it is finite. And then we have that A is contained in the union over all finite B0 subset of B, A intersection the closure of B0. Now each of these is finite, and we're going over all finite subset of B, and we assume that B is infinite, which by basic cardinality argument implies that the cardinality of A is less or equal than the cardinality of B. This concludes the proof of 2, and item 3 is immediate from 2. So this concludes the proof of the replacement lemma. Thanks to the replacement lemma, we define if Y is a subset of D, a strongly minimal set, or just a pregeometry, then the dimension of Y is the cardinality of a basis for Y. And we have just proved that all bases of a given set have the same cardinality. Our next aim in the following lecture will be to show that just like for vector spaces of algebraically closed fields, the dimension of a strongly minimal structure determines its isomorphism type. So we will show that if T is a strongly minimal theory and Mn are two models of T, then M is isomorphic to N if and only if the dimension of M is equal to the dimension of N with respect to the pregeometry given by the algebraic closure operator. This theorem will have the following immediate corollary. If T is strongly minimal and the language L is countable, then T is kappa categorical for every uncountable kappa. And moreover, T has at most countably many countable models. Let us quickly deduce this from the stated theorem proof. So assume that T is countable, so the language is countable. Then, as we have remarked earlier, the cardinality of the algebraic closure of any set A in the model of T is at most the cardinality of A plus aleph naught. Hence, any basis for M where M is a model of T of cardinality kappa strictly greater than aleph naught has cardinality kappa. Hence, any two models of T of uncountable cardinality kappa have the same dimension, and so the theorem can be applied to conclude that they are isomorphic. And similarly, if M is a countable model, then the dimension of M is also at most countable. And so there are countably many possible choices for the dimension of a countable model of T, which corresponds to at most countably many different isomorphism types for the countable models of T.